Let me ask you a question. What is the most rebellious substance in the universe? What is the one material that looks at the laws of physics, the nice, clean rules that everything else follows, and says, no, I don't think I will? You might guess something exotic, some rare element cooked up in the heart of a supernova, some bizarre plasma or some strange quark matter. But no, the answer is sitting in a glass on your kitchen table right now. It's water, plain old water. And I want to tell you something that may disturb you. The more I have studied water, the more unsettled I have become. Because water doesn't just bend the rules a little, it shatters them. It does things that, by every reasonable expectation of chemistry and physics, it simply should not be able to do. And the fact that it does these impossible things is the only reason you and I are here to talk about it. So by the end of today, I want you to understand something that most people never think about. I want you to see that water is the strangest liquid on the planet, that its weirdness is not some minor footnote in a chemistry textbook. It is the very foundation of life itself. And I want you to understand why, when you really dig into the physics, the explanation is beautiful but deeply unsettling. Because it means the universe is balanced on a knife's edge. A knife's edge made of hydrogen bonds. All right, let's start with something you've seen 1,000 times. You drop an ice cube into a glass of water. What happens? It floats. You've seen this since you were a child. It's so ordinary you don't even think about it. You'd never dream of calling it remarkable. But let me tell you, if you showed that to a chemist from another planet, a chemist who had studied every other substance in the universe but had never seen water, that chemist would faint. That chemist would look at you and say, that is impossible. Solids do not float in their own liquid. That violates everything I know about matter. And the alien chemist would be absolutely right to be shocked, because here is the rule that virtually everything else in the universe follows. When a liquid freezes and becomes a solid, it gets denser. The molecules slow down. They pack together more tightly. The solid form is heavier than the liquid form per unit volume. And so the solid sinks. Think about it. When you melt iron and pour it into a mold and let it cool, the solid iron sinks to the bottom of any remaining liquid iron. When you freeze alcohol, the solid sinks. Mercury, gold, copper, bismuth, nitrogen, oxygen, sulfur, you name it. The solid sinks in the liquid. That's the rule. It's one of the most reliable patterns in all of chemistry and physics. Water says, not me. When water freezes, it expands. It gets about 9% bigger. Think about what that means. 9% is not trivial. It's enough to burst iron pipes. It's enough to crack granite boulders. It's enough to split a sealed glass bottle in your freezer, and I bet some of you have learned that the hard way. All of that destructive power comes from the simple fact that water, unlike almost everything else in the universe, gets bigger when it gets cold enough to solidify. And because ice is less dense than liquid water, it floats. Now, I said that sounds like a small curiosity. Let me show you why it is anything but small. Let me show you what would happen if water behaved like a normal, respectable substance. Imagine a lake in winter, a big, deep lake. The air above it is getting colder and colder. The surface of the lake cools down first, because it's in contact with the cold air. Now, with a normal liquid, the cold surface layer would become denser than the warmer water below, and it would sink. Warmer water from below would rise up to take its place. And that warmer water would cool too, and sink. This is convection, and it would keep going, mixing the lake, cooling the whole body of water gradually and uniformly from top to bottom. Eventually, the entire lake would reach the freezing point. And then what? The first ice crystals would form. Being denser than the liquid, they would sink to the bottom. More ice would form at the surface, and it too would sink. The lake would freeze from the bottom up, layer after layer. Every fish, every plant, every tadpole, every bacterium, every microscopic creature entombed in a solid block of ice, dead. All of them. And in the spring, when the sun came back, the ice at the bottom of the lake would be insulated by the water above it. It would be extraordinarily slow to melt. Some of it might never melt. Year after year, more ice would accumulate at the bottom. The oceans, in their shallower regions, would suffer the same fate. Over geological time, vast quantities of the planet's water would be locked away in permanent ice at the bottom of every body of water. Life in the water would be impossible, and since life began in the water roughly 3.5 billion years ago, well, there would be no life at all. No fish, no amphibians, no dinosaurs, no mammals, no humans. An empty, frozen world. And it gets worse. Think about what that bottom ice does to the planet's heat balance. Ice is white. It reflects sunlight back into space. Normally, dark ocean water absorbs sunlight and warms up. But if the sea started accumulating ice at the bottom, eventually that ice would build up to the surface. Now you've got vast white sheets reflecting sunlight instead of absorbing it. The planet cools further. More ice forms, more reflection, more cooling. It's a runaway feedback loop, what climatologists call the ice albedo feedback. Without the density anomaly of water, the Earth might have tipped into a permanent deep freeze very early in its history. A snowball planet, white and silent and dead. You might say, well, surely the tropics would stay warm. Maybe. But without liquid oceans to moderate the climate, without water's enormous heat capacity acting as a thermal buffer, the temperature swings even near the equator would be savage. And without liquid water to dissolve nutrients and carry them around, the chemistry of life has nothing to work with. No medium, no solvent, no life. So this one anomaly, ice floating, is not just a curiosity. It is arguably the single most important physical property of any substance on Earth, and it comes from water's refusal to obey the rules. But water doesn't stop there with just one act of rebellion. Here's what really happens, and it's so clever it almost seems designed, although I hasten to add that's not a scientific statement. Water gets denser as you cool it, just like any well-behaved liquid, but only down to 4 degrees Celsius. At 4 degrees, water reaches its maximum density. That's the point where it's heaviest. And then something deeply strange happens. You cool it further from 4 degrees down towards 0, and instead of continuing to contract, water starts to expand. It gets lighter. The colder it gets below 4 degrees, the less dense it becomes. You see what this does? The coldest water, the water that is closest to freezing, is lighter than the water below it. So it stays at the surface. It doesn't sink. The warm, dense water at 4 degrees settles to the bottom and stays there. So the lake freezes from the top down, not the bottom up. A layer of ice forms on the surface. And here's the beautiful part. Ice is a terrible conductor of heat. That floating lid of ice acts like a blanket, an insulating cap, protecting the liquid water beneath from the frigid air above. The deep water stays at roughly 4 degrees. The fish survive. The plants survive. Life goes on beneath the ice, calmly waiting for spring. All because water has this one peculiar rule-breaking property. If you are not amazed by this, I haven't done my job. Now, you might say, all right, that's one weird thing about water. Interesting. But maybe it's just a fluke. Oh, but it's not just one thing. The ice floating business is only the first item on a long list of misbehaviors. Let me go through the charges. Let's talk about boiling. Here's a fact that should bother you more than it probably does. Water boils at 100 degrees Celsius. You know that. Everybody knows that. But do you know how absolutely insane that number is? Water is a small molecule. 1 oxygen atom, 2 hydrogen atoms, H2O. Its molecular weight is only 18. That's tiny. Now, oxygen belongs to a family of elements in the periodic table, a group we call group 16. The elements below oxygen in this group are sulfur, selenium, and tellurium, and each of them forms a compound with hydrogen, just like water. Sulfur gives you hydrogen sulfide, H2S, the stuff that smells like rotten eggs. Selenium gives you hydrogen selenide, H2Se. Tellurium gives you hydrogen telluride, H2Te. Now here's where the pattern should work. H2S boils at minus 60 degrees Celsius. H2C boils at minus 42 degrees. H2T boils at minus 2 degrees. Do you see the trend? As the molecules get heavier, they boil at higher temperatures. That makes perfect sense. Heavier molecules have more electrons. More electrons means stronger London dispersion forces, those weak but universal attractions between all molecules. More stickiness, higher boiling point. Nice, clean, predictable. Now, if you extrapolate this trend upward to the lightest member of the family, the molecule with the fewest electrons and the lowest molecular weight, you'd predict that water should boil at something like minus 70 or minus 80 degrees Celsius, way below zero. Water should be a gas at room temperature. Instead, water boils at plus 100 degrees Celsius. It is not just off the trend, it is off the planet. The gap between the predicted boiling point and the actual boiling point is roughly 170 degrees. That's not a small error. That's a colossal disagreement between theory and reality. If you predicted a building would be 2 stories tall and it turned out to be 50 stories tall, you'd say something is very, very wrong with your prediction. Or something is very, very unusual about that building. And it's not just the group 16 family. You see the same pattern with the hydrides of nitrogen and fluorine. Ammonia, NH3, and hydrogen fluoride, HF, both have abnormally high boiling points compared to their heavier cousins. The pattern is the same. The lightest member of each family has a wildly elevated boiling point. Something special is happening when hydrogen teams up with oxygen, nitrogen, or fluorine. And that something is the hydrogen bond. But I'm getting ahead of myself. We'll come to that. And think about what this means. If water boiled where chemistry says it should, at minus 80 or so, there would be no liquid water on the surface of the Earth. Not at room temperature. Not anywhere except maybe the coldest craters of the polar ice caps. The oceans wouldn't exist. Rain wouldn't exist. Rivers, lakes, clouds, fog, dew, none of it. And you, who are roughly 60% water by mass, certainly wouldn't exist. Something is making water molecules cling to each other with extraordinary, unreasonable tenacity. Something is giving water an absurdly high boiling point for a molecule of its size. Hold that thought. Now let's talk about heat. Suppose you put a pot of water on the stove. You turn the flame on. You wait. And you wait. And you wait some more. It takes a long time to boil water, doesn't it? Much longer than you'd expect. There's a reason for that. Water has a bizarrely high specific heat capacity. What that means in plain language is that water is a glutton for energy. You can pour heat into water, and its temperature goes up only slowly, reluctantly, as if the water is absorbing all that energy and hiding it somewhere. Let me give you a comparison. Take the same mass of iron, put the same amount of heat into the iron. The iron's temperature shoots up almost 10 times faster than the water's. Iron is easy to heat. Copper is even worse. Sand, rock, air, all of them heat up faster than water by large margins. Water absorbs heat energy and just sits there, barely warming up, like a fat cat in the sun that refuses to move. It soaks up energy like a sponge, soaks up water, if you'll forgive the circular metaphor. Now, why does this matter? It matters enormously. It's the reason the ocean moderates the climate of the entire planet. Coastal cities don't get as hot in summer or as cold in winter as cities far inland. The ocean acts as a vast thermal battery, absorbing tremendous quantities of heat in summer without heating up too much, and releasing that heat slowly in winter. Without water's anomalous heat capacity, the temperature swings between day and night, between summer and winter, would be savage. Life on land would be far more difficult, perhaps impossible. And your body uses the same trick. You are, as I said, about 60% water. That water stabilizes your internal temperature. When you exercise, your muscles generate heat. If your body were made of something with a normal specific heat, you'd cook yourself alive every time you ran for a bus. But all that water absorbs the excess heat, keeping your temperature stable. Then you sweat, and the water evaporates, and that carries the heat away. Which brings me to yet another anomaly. Water has an extraordinarily high heat of vaporization. That means it takes a lot of energy to turn liquid water into steam, much more than you'd expect for a molecule of its size. When sweat evaporates from your skin, each gram of water that escapes carries away about 540 calories of heat. That's a lot. That's why sweating cools you so effectively. If water had a normal heat of vaporization, sweating would be almost useless as a cooling mechanism. Let me keep going. Water has the highest surface tension of any common liquid except mercury. Surface tension is what makes water form droplets instead of spreading into a thin film. It's what lets you carefully place a steel sewing needle on the surface of water and watch it float, even though steel is almost 8 times denser than water. The surface of the water acts like a stretched membrane, an elastic skin, and something is pulling those surface molecules together with unusual force. This same surface tension drives capillary action. If you dip a thin glass tube into water, the water climbs up the tube against gravity. The narrower the tube, the higher it climbs. This seems like magic. Water is going uphill with no pump, no energy input that you can see. How? The water molecules at the edge of the tube are attracted to the glass. They form hydrogen bonds with the silicon and oxygen atoms in the glass surface. So the water at the edge creeps upward, wetting the glass. But as that edge water rises, it pulls on the water behind it through the network of hydrogen bonds within the liquid. Surface tension holds the column together. The result is a column of water that climbs the tube until the weight of the column exactly balances the upward pull of adhesion and surface tension. This is how trees work. Let that sink in. A giant redwood, 300 feet tall, pulls water from its roots to its topmost needles entirely by capillary action and transpiration. There are no pumps, no hearts, no mechanical devices, just tiny channels in the wood, capillaries, and the relentless pull of water's surface tension and hydrogen bond cohesion. Water clings to the walls of those channels, and the evaporation of water from the leaves at the top creates a suction that pulls the whole column upward. If water had a normal surface tension, this wouldn't work. Trees couldn't exist above about 5 or 10 feet. There would be no forests, no jungles, no ecosystems built around large plants. The land surface of the earth would look completely different, and the species that depend on forests, which is most species, would never have evolved. Water is also an exceptional solvent. More substances dissolve in water than in almost any other common liquid. This is why water is sometimes called the universal solvent, although that's a slight exaggeration. The reason is, again, water's polarity. Those slightly positive and slightly negative ends of the water molecule can surround and pull apart ionic compounds like table salt and can form hydrogen bonds with many other molecules, keeping them in solution. The biochemistry inside your cells depends absolutely on water's ability to dissolve and transport an enormous variety of molecules. So let me take stock. Here is the charge sheet against water. It expands when it freezes. It boils at an absurdly high temperature. It has a freakishly high specific heat. It has a freakishly high heat of vaporization. It has a freakishly high surface tension. It's an abnormally good solvent. and every single one of these anomalies is essential for life on Earth. Now, here is the question that any self-respecting physicist must ask. Is there one explanation for all of this, or do we need 6 different explanations? This is the beautiful part. There is one explanation, one single underlying mechanism that accounts for every one of these strange behaviors, and it's called the hydrogen bond. Let me build this up carefully, because it deserves to be understood properly. A water molecule is shaped like a boomerang. The oxygen atom sits at the bend, and the 2 hydrogen atoms stick out at an angle of about 104.5 degrees. It's not a straight line. It's bent, and that bend is critical. Now, oxygen is a very greedy atom when it comes to electrons. Chemists call it highly electronegative. Among the common elements, only fluorine is more electronegative. What this means is that oxygen pulls the shared electrons in the OH bonds toward itself. It hogs the electron cloud. This leaves the hydrogen ends of the molecule slightly electron poor, slightly positive. And it leaves the oxygen end, electron rich, slightly negative. The water molecule is what we call a polar molecule. It has a plus side and a minus side, like a tiny bar magnet. When you have a bunch of these polar molecules near each other, the positive hydrogen on one molecule feels an attraction to the negative oxygen on a neighboring molecule. This attraction is what we call a hydrogen bond. Now wait, I need to be careful here, because the name is misleading. A hydrogen bond is not a regular chemical bond. The covalent bond that holds the atoms together inside a single water molecule, the OH bond, is strong. It takes a lot of energy to break. A hydrogen bond is maybe 1/20th as strong as a covalent bond. It's relatively weak. But, and this is the crucial distinction, it is much, much stronger than the ordinary van der Waals forces, the London dispersion forces, that hold most other liquids together. A hydrogen bond is in a middle category, not as strong as a real bond, but 10 or 20 times stronger than the flimsy forces that hold together a liquid like, say, hydrogen sulfide. And here's the thing that makes water special. Each water molecule can form not 1, not 2, but up to 4 hydrogen bonds simultaneously. 2 through its 2 hydrogen atoms acting as donors. 2 through the 2 lone pairs of electrons on the oxygen acting as acceptors. 4 bonds per molecule. 4 sticky hands reaching out and grabbing 4 neighbors. And those neighbors are doing the same thing. Each of them grabs 4 others. And those grab 4 more. The result is a 3-dimensional network of hydrogen bonds threading through the entire liquid. Every molecule is connected to its neighbors, and those neighbors are connected to their neighbors, forming a vast, constantly shifting, flickering web of connections. In most liquids, the molecules are held together by weak forces, and they slosh around almost independently. In water, there's this web, this network, this scaffolding of hydrogen bonds that gives the liquid an unusual degree of internal structure and cohesion. Now let me explain this in the simplest possible way, as if I were talking to a bright 12-year-old. Because when you can do that, you know you truly understand something. Imagine a dance hall full of people. In a normal liquid, the dance is casual. People mill around, bump into each other gently, drift apart. There's a mild attraction. They'd rather be in the hall than outside, but nobody's really holding on to anyone. That's a normal liquid. Water is a very different dance. In water, everyone is holding hands with 4 other people at all times. You're connected. The whole room is connected. If someone tries to pull one dancer out of the room, they can't just grab them and go. They have to break 4 handshakes first. And as soon as one handshake breaks, the dancer's free hand grabs someone else's hand. The network keeps reforming. You have to work very hard to separate anyone from the group. That's why water's boiling point is so high. To send a water molecule into the gas phase, you have to break its hydrogen bonds, rip it away from the network, and that takes a lot of energy. Now, why does ice float? This is lovely. When water freezes, the hydrogen bonds don't just let the molecules pack together in any old arrangement. They force them into a very specific structure. It's a hexagonal lattice, a repeating pattern of 6-membered rings, like a honeycomb. And here's the key. This crystal structure has holes in it. The hydrogen bonds hold the molecules at arm's length, arranged in those hexagons, with empty space in the center of each hexagon. In liquid water, the situation is different. Some hydrogen bonds are broken at any given moment. The molecules can jostle, rotate, and slide past each other. They fill in the gaps. They're closer together on average than they are in ice. So liquid water is actually denser than ice because the liquid, despite being warmer and more chaotic, has its molecules packed more tightly. The order creates space, the disorder fills it in. That's why ice floats. And I find that poetic. The rigid crystalline structure of ice is more open, more spacious than the chaotic tumble of liquid water. Organization makes it lighter. Chaos makes it heavier. That's exactly backwards from what your intuition might tell you. And the high specific heat? The hydrogen bonds act as energy sinks, like tiny shock absorbers. When you pour heat into water, a lot of that energy goes into wiggling, stretching, bending, and breaking hydrogen bonds, rather than into speeding up the molecules. And the speed of the molecules is what we measure as temperature. So the hydrogen bonds absorb heat energy, storing it in the network without letting the temperature rise quickly. It's like pouring water into a bucket with holes in it. A lot of the water leaks away before the bucket fills up. The high surface tension? At the surface, water molecules can only form hydrogen bonds with their neighbors below and to the sides. There are no molecules above them, so they're missing some bonds. To compensate, the surface molecules pull together extra tightly, clinging to each other, creating a strong elastic skin across the top of the liquid. Every anomaly, every single one. The same explanation, hydrogen bonds. Now let me address a misconception that I think is genuinely dangerous. A lot of people, including many science students, think water is a simple substance. It's H2O, 3 atoms. One of the smallest molecules you can make. How complicated can it be? This is profoundly wrong. Water is one of the most complex and poorly understood liquids in all of science. I am not exaggerating even slightly. There are entire scientific conferences devoted solely to the study of water. There are researchers who have spent 30 and 40 years trying to understand the internal structure of liquid water, and they will tell you honestly that they haven't finished. There is a website maintained by a scientist in London that catalogs the known anomalous properties of water. Last I checked, the list had over 70 entries. 70 things that water does differently from what you'd expect. 70 rule breakings for what is supposed to be a simple molecule. The problem is the hydrogen bond network. In liquid water, hydrogen bonds are constantly forming and breaking on a time scale of about 1 picosecond. That's 1/1,000,000th of a second. A million times per second, the network is rearranging itself. At any given instant, roughly 80 to 90% of the possible hydrogen bonds are intact, and the rest are broken. But which ones are intact and which are broken changes constantly. The network is alive, in a manner of speaking. It breathes and flexes and restructures itself faster than anything you can imagine. What this means is that liquid water is not a uniform substance. At the molecular level, it's a mosaic. Some regions, at any given moment, have molecules in orderly, almost ice-like arrangements, with most hydrogen bonds intact. These are called low-density patches because the ice-like arrangement is open and spacious. Other regions are more disordered, with broken bonds and molecules packed closely together. These are high-density patches. The liquid is a constantly shifting mixture of these two kinds of local environment, and the balance between them depends on temperature. At high temperatures, the disordered high-density arrangement dominates, and water behaves more or less like a normal liquid. But as you cool the water, the orderly low-density patches grow larger and more prevalent. This is when the anomalous behaviors really start to kick in. The density maximum at 4 degrees, the expansion on further cooling, the increasing specific heat, all of it becomes more dramatic as the water gets colder and the hydrogen bond network becomes more structured. Some scientists have even proposed that deep in the supercooled region, at temperatures below the normal freezing point, where water can remain liquid if cooled very carefully, there might be an actual phase transition between two distinct liquid phases of water, a high-density liquid and a low-density liquid. Two kinds of water. This is called the liquid-liquid critical point hypothesis, and it's still being debated vigorously. We don't know for certain if it's true, and I like that. I like it when nature reminds us that something as common as a glass of water still holds genuine mysteries. All right. Let me take you through a thought experiment now. This one is fun, and it involves a genuine scientific puzzle. Imagine you have two identical glasses, same size, same shape, same material. You fill one with hot water, let's say 90 degrees Celsius, just below boiling. You fill the other with lukewarm water, about 30 degrees. You place them both into a freezer at the same time, side by side, same shelf, same position, same everything. Which one freezes first? You'd say the lukewarm one, obviously, right? It has a head start. The hot water has to cool all the way down to 30 degrees before it's even in the same position as the lukewarm water. After that, it still has to do everything the lukewarm water has to do. The hot water has to run a longer race. It must finish last. This seems like pure logic, but sometimes it doesn't work out that way. Sometimes the hot water freezes first. This is called the Mpemba effect, and it's one of the most persistent puzzles in everyday physics. It's named after Erasto Mpemba, a Tanzanian schoolboy who, in the early 1960s, was making ice cream in his cooking class. The recipe said to heat the mixture, let it cool, and then put it in the freezer. Mpemba was in a hurry. He skipped the cooling step and put his hot mixture straight into the freezer. To his astonishment, his ice cream froze before his classmates' cooled mixtures did. He asked his teacher to explain. The teacher said, "That is Mpemba physics, not universal physics," which is a wonderful put-down but a terrible scientific attitude. And it tells you something about the danger of being too sure you know how the world works. Mpemba didn't give up. And here's what I love about this story. He was just a schoolboy. He had no laboratory. He had no funding. He had nothing but curiosity and stubbornness. And those are the two most important tools in all of science. When a physics professor named Dennis Osborne visited his school, Mpemba asked him the question. Osborne had the wisdom and the intellectual honesty not to laugh. He went back to his lab and tested it. He put containers of water at different temperatures into a freezer and measured. And to his surprise, the hot water sometimes did freeze first. Osborne and Mpemba published their findings together in a physics journal in 1969. Now, Mpemba was not the first to notice this. Aristotle wrote about it around 340 years before Christ. Francis Bacon mentioned it. René Descartes mentioned it. But nobody had done a proper experiment until this schoolboy from Tanganyika insisted on being taken seriously. Now, this seems to violate common sense. It seems to violate thermodynamics. Let me be honest with you. Some very careful experiments have failed to reproduce the Mpemba effect. Some researchers have published papers arguing that it's an artifact, the result of evaporation, different convection currents, dissolved gases, the thermostat behavior of the freezer, and other confounding variables. There's a paper from about 20 years back that looked at it very carefully and concluded, somewhat sadly, that there's no good evidence for the effect under controlled conditions. And yet, other experiments do observe it, and A number of theoretical explanations have been proposed, several of them quite plausible. One explanation involves evaporation. Hot water evaporates faster. This reduces the total mass of water in the container, and less water freezes faster. Simple, but it only accounts for some of the effect. Another involves convection. Hot water has stronger convection currents because of larger temperature gradients. These currents can distribute the cooling more efficiently, getting more of the water to the freezing point faster. But the most fascinating explanation, from our perspective, involves hydrogen bonds. When you heat water, you don't just make the molecules move faster. You change the structure of the hydrogen bond network. You break bonds, you rearrange clusters, you alter the distribution of strong and weak hydrogen bonds. There is evidence that hot water has a different configuration of hydrogen-bonded clusters than cold water, and that some of these configurations are actually better seeds for ice crystal nucleation. Let me say that again, because it's important. Heating water doesn't just add energy, it restructures the molecular network. And when you cool that restructured water back down, it may take a shortcut to crystallization that the lukewarm water with its different network structure cannot take. A glass of water, in a sense, remembers where it has been, not in any mystical way, in a physical, structural, molecular way. The arrangement of hydrogen bonds carries information about the water's thermal history, and that information can influence how it behaves when you cool it. This is not settled science. Let me be clear about that. We do not have a definitive explanation for the Mpemba effect. It remains one of those embarrassing reminders that we don't fully understand the most common liquid on Earth. Now I want to take you one level deeper, into the quantum realm, because so far everything I've told you is classical in the sense that it's about molecules, bonds, structures, and energies. It's the kind of physics Newton would recognize in spirit, even if the details would surprise him. But water has quantum secrets, and this is where things get really extraordinary. Remember the hydrogen bond. An oxygen atom on one molecule, an oxygen on a neighbor, and a hydrogen atom in between bonded covalently to one oxygen and hydrogen bonded to the other. That hydrogen atom is really just a proton with a single electron around it. The proton is the nucleus. Now, this proton sits in an energy landscape that has two wells, two low spots. One is close to its own oxygen, where it belongs. The other is close to the neighboring oxygen on the other side of the hydrogen bond. Classically, the proton stays in its own well. It doesn't have enough energy to hop over the barrier between the two wells. But here's where quantum mechanics changes everything. Protons are very light, and quantum mechanics tells us that light particles are not really particles in the ordinary sense. They're also waves. They have a probability of being found in different places. And a light particle facing a thin energy barrier can do something that has no classical explanation at all. It can pass through the barrier without ever having the energy to go over the top. This is quantum tunneling. You know, this works for electrons. It's the basis of tunnel diodes and scanning tunneling microscopes. But protons are about 2,000 times heavier than electrons. They're much harder to tunnel. The probability of tunneling drops exponentially with the mass of the particle. So you'd think protons are too fat to tunnel, if you'll excuse the expression. And yet, in water and ice, it happens. Protons tunnel through the hydrogen bond barrier, flickering from one side to the other. The reason is subtle. The barrier is thin, only about 1 angstrom, a tenth of a billionth of a meter. And while protons are heavy compared to electrons, they're still light compared to, say, an oxygen atom or a nitrogen atom. They're the lightest nucleus there is. Just barely light enough for quantum mechanics to get a foothold. And it gets more remarkable still in ice, where the molecules are locked in that rigid hexagonal lattice. The tunneling doesn't happen to just one proton at a time. That would be simple enough. No. Experiments have shown that in rings of 6 water molecules, which are the basic structural unit of the ice hexagonal lattice, all 6 protons can tunnel simultaneously. They all switch positions at the same instant, in a coordinated, concerted quantum motion. It's like a quantum square dance, where every dancer simultaneously swaps partners, all at once, without any of them passing through the space in between. Why does it happen this way? Because if just one proton tunneled by itself, it would create what's called a defect in the crystal, a violation of the ice rules. The ice rules say that each oxygen must have exactly 2 protons near it, one from its own molecule and one from a neighbor's hydrogen bond. If one proton hops, one oxygen ends up with 3 protons and another with only 1. That costs a lot of energy. But if all 6 protons in a ring hop together, the ice rules are preserved everywhere. Nobody ends up with too many or too few protons. It's the only way to do it without paying an energy penalty. So quantum mechanics, in a sense, is enforcing a rule by breaking another rule. The protons can't hop individually because that violates the crystal's local charge balance. They can only hop collectively. And collective tunneling is a many-body quantum effect. It's not one particle doing something odd. It's 6 particles acting in perfect coordination, quantum mechanically entangled. This kind of correlated many-body quantum behavior is usually only seen in very exotic systems: superconductors, superfluid helium, Bose-Einstein condensates, the things that win Nobel Prizes. Some physicists have found evidence that below about 20 Kelvin, that's minus 253 degrees Celsius, the dielectric properties of ice, how it responds to electric fields, show signatures of this collective quantum tunneling of protons. And this is a macroscopic quantum phenomenon, meaning the quantum behavior of individual protons adds up to an effect you can measure on a chunk of ice with ordinary laboratory equipment. Here's the deep part. Protons are fermions. They obey the Pauli exclusion principle, which says no 2 identical fermions can occupy the same quantum state at the same time. So how can 6 protons tunnel together? The proposed answer is that the protons pair up. A pair of protons can act as a boson, and bosons do not obey the Pauli exclusion principle. Bosons can pile into the same state. Boson condensation is exactly what happens in superconductivity, where electrons pair up into Cooper pairs and all drop into the same ground state, giving rise to 0 electrical resistance. So ice, at very low temperatures, is doing something that has a deep kinship with superconductivity. Not in any practical sense. Nobody is going to make a water-based superconductor. But the underlying quantum mechanism, the pairing of fermions into bosonic pairs to enable collective quantum behavior, is the same trick nature uses in both cases. The universe is economical with its ideas. When it finds a good trick, it uses it over and over in contexts you'd never expect. Now let me tell you why all of this matters beyond physics. Water is, so far as we can tell, the only liquid with this particular combination of anomalous properties. Other substances have 1 or 2 oddities. Silicon and germanium expand slightly when they freeze. Gallium does the same. But none of them have the full package. None of them combine the density anomaly, the extraordinary boiling point, the high specific heat, the high heat of vaporization, the surface tension, the solvent properties, the hydrogen bond network, and the quantum effects, all in one substance. And I've tried to show you that every single one of these properties is essential for life. Let me trace the connections one more time, carefully, because this matters. The high boiling point keeps water liquid over the temperature range that exists on Earth's surface. Without it, there's no ocean, no rain, no rivers. The planet is dry as the moon. The density anomaly keeps lakes from freezing solid in winter. Without it, aquatic life cannot survive in temperate and polar regions. the freshwater ecosystem collapses. The high specific heat stabilizes the climate and prevents wild temperature swings between day and night, between summer and winter. Without it, the surface of the earth is a furnace by day and a freezer by night. The high heat of vaporization makes evaporative cooling, sweating and transpiration effective enough to keep organisms alive during exertion or in hot climates. Without it, warm-blooded creatures overheat and die. The high surface tension drives capillary action, which is how trees pull water from their roots to their crowns, hundreds of feet straight up against gravity. Without it, large land plants can't exist, and the ecosystems built around forests collapse. The solvent properties allow the incredibly complex biochemistry inside your cells. Proteins fold in water. Enzymes catalyze reactions in water. DNA replicates in water. Nutrients dissolve and travel through water. Without water's ability to dissolve such a vast range of substances, the chemistry of life simply wouldn't work. This is why, when astronomers look for life on other worlds, the first question they ask is there liquid water? Not because we lack imagination, not because life absolutely must use water, but because no other known substance provides all of these functions simultaneously. Ammonia has been proposed as a possible alternative solvent for life. So has liquid methane, which exists on Saturn's moon Titan. But neither ammonia nor methane has the right combination of properties. Ammonia has a much narrower liquid range. Methane has essentially no polarity, so it's a poor solvent for the complex molecules that biology seems to require. Water is unique. There is nothing else like it. And all of these remarkable properties trace back to the same cause: the electronegativity of oxygen, the lightness of hydrogen, the bent shape of the water molecule, and the resulting ability to form a dense, dynamic, three-dimensional network of hydrogen bonds. Change any one of these underlying factors significantly, and the whole house of cards comes down. Now, some people look at all of this and say it proves the universe was designed for life. I understand that impulse. The fit seems too perfect to be accidental, but I think the honest scientific answer is more interesting and more humble. We don't know why the constants of nature are what they are. We don't know why the electron has the charge it has, or why the strong force has the strength it has, or why the periodic table has the structure it has. We can say that the laws are what they are, and one consequence of those laws is this extraordinary molecule, and one consequence of this extraordinary molecule is us. I find that both thrilling and disturbing, because it means we don't understand the deepest reason, and if someone tells you they do, well, I'd be polite, but I'd also be skeptical. There's one more thing I want to say, and it's about the nature of scientific understanding itself. Water is the most common substance on the surface of this planet. It covers 70% of the globe. You interact with it dozens of times a day. You'd think it would be the most thoroughly understood substance in all of science. And yet, as I've tried to show you, water remains deeply, genuinely, sometimes embarrassingly mysterious. We still argue about the Mpemba effect. We still debate the two-structure model of liquid water. We are still discovering quantum tunneling effects in ice. There are serious physicists who have devoted their entire careers to water, and they will tell you plainly that there is much we do not understand. The most familiar thing in the world is still teaching us physics. That is humbling, and it should make you suspicious of anyone who claims that the interesting problems are all solved. They are not. They never are. Some of the deepest puzzles are hiding in the most ordinary places, not in black holes or quarks, but in a glass of water on your table. Let me tell you what I find most extraordinary about all of this. It's not any single anomaly. It's the fact that all of these anomalies come from one source, one mechanism, one trick of nature, the hydrogen bond. And the hydrogen bond comes from the electronegativity of oxygen and the lightness of hydrogen. And those come from the fundamental structure of the atom, the number of protons in the nucleus, the arrangement of the electron shells, which comes from the strength of the electromagnetic force and the mass of the electron. So you pull a thread and it goes all the way down, all the way to the deepest level of physics. The reason ice floats in your drink is ultimately a consequence of the charge of the electron and the structure of quantum mechanics. The reason you're alive is that the fundamental constants of nature happen to be precisely the values that produce a molecule with extraordinary rule-breaking properties. Not a little bit extraordinary. Wildly, almost absurdly extraordinary. Could it have been otherwise? Could the constants have been different? Would life have found another way? These are among the deepest questions in all of science, and they remain unanswered. I don't mind that we don't have the answer. In fact, I prefer it that way, because an unsolved problem is an invitation to think, and an invitation to think is the greatest gift the universe offers us. So the next time you pick up a glass of water, the next time you watch ice cubes floating and clinking, the next time you feel the cool of evaporating sweat on a hot day, or watch rain sliding down a window, or see a spider walking on the surface of a pond, I want you to feel a chill that has nothing to do with the temperature. I want you to feel the strangeness, feel the depth. Because water, the simplest, most familiar, most essential substance you will ever touch, is a defiant rebel against the laws of physics. And without that rebellion, you would not be here to wonder about it. Now here's my question for you, and I genuinely want to know what you think. If water obeyed all the normal rules, if it shrank when it froze and boiled at minus 80 degrees and had a normal specific heat, do you think life would have found some other way? Would chemistry have invented a different miracle molecule? Or would the universe be dark and silent and empty? Tell me your answer.